We are coming back here. First talk of this last session is by Fabiana Laguna from the Centro Atómico Bariloche, Argentina, that will talk about optimal risk in wealth exchange model. So, Fabiana, all yours.
Thank you, Celia. And I will first like to thank the organizers and you, Celia, particularly for the invitation, which gives me the opportunity to share this work with you. And the results are, okay, this is working now. Okay, the results I am going to show you today are part of the degree thesis of my former student, Julian Neñer. In particular, I'm going to present the first of the work we published together. And the motivation of this work is something that everyone knows, that is the different countries around the world exhibit high and equal wealth distribution, in which about 20% of the populations own more than 80% of the total wealth of individuals. And as you know, this phenomenon has been observed in many societies at different scales and in all the times. More than a century ago, the economist Wilfredo Pareto found repeating patterns describing power laws in the wealth distribution of different European countries. And the exponents of this distribution, nowadays referred as Pareto index or Pareto exponent, is a simple way to measure inequality. Later studies established that this power law are only observed within the higher classes of population, while the poorest individuals show log normal, Gibbs, or exponential distribution. In order to have a deeper understanding of social behavior that leads to this kind of unequal wealth distribution, several simple models based on ensembles of economic agents have been proposed for the past decades. These models are based on stochastic wealth flow processes between entities, where their time evolution is given by certain trading rules. In particular, year sale model and merger spin-off models, also referred as fair and loser rules, have become quite popular as they have shown promising results replicating empirical data. However, and as far as we know, the microscopic behavior has not been studied in the same detailed manner. And in particular, the name of merge spin-off model refers to two mechanisms. The spin-off mechanism, through which a new company emerged from an existing and more important one, and the merge or fusion mechanism that in which two companies join together by combining their assets. In the year-set model, agents interact by putting an arbitrary fraction of their assets at risk, and the name is inspired by garden or garage sales, in which they transfer the wealth, and this occurs through the realization of good or bad transaction between sellers and buyers. So our purpose is to address a more in-depth study regarding the microscopic aspect of these multi-agent models in order to analyze whether the success or failure of the economic agents are determined by the model parameters. So today I am going to focus only in the year-set model because I have no time, but also because it's the one with most interesting results at the macroscopic level. And here it's worth mentioning to in a previous work, Brian Hayes looked into some of these aspects and, for example, find that the first few transactions performed in the year-set model can determine the wealth positions of the agents for subsequent times. This is a result that we also obtained and analyzed, but I will not discuss here because I have not enough time. But I rather explain how this model works. Agents are endowed with wealth, which will change during the exchange process, and a risk that will remain in this version fixed during the process. The dynamics of the system for two agents that are selected at random will be given by this expression, where eta is a random variable that can take values 0 or 1. And this is the amount of wealth transferred in a single transaction. This quantity defines the particular model, and in this case corresponds to the minimum stake among the partners. In this way, no agent can lose all their goods in a single transaction. And this is the reason why this model is also called the fair rule. Note also that this factor, the risk factor, determines the behavior of the agent. And also note that the total wealth of the system will be conserved in all the times. It has been proven that this model, for this model, the only possible macroscopic equilibrium is the condensation of wealth in a few agents. And to alleviate this effect, it is usual to add an asymmetry to the distribution of eta in order to favor the poorest of the two agents of the transaction. And this is called the social protection factor. When this factor is 0, this probability is 1.5, and both agents have the same chances of winning, while for large F, the poorest agent has the highest chances of winning the bet. So the macroscopic equilibrium, as you can imagine, is highly dependent on this parameter, as the wealth inequality between agents decreases with increasing F, and this changes the resultant wealth distribution, as it will be clear in a minute. So to measure how unequal is a wealth distribution of a certain society, the Gini index is commonly used. In this context, it can be easily calculated, given n individuals. It is defined as the mean absolute difference between their wealth. And from this expression, it's easy to conclude that Gini equal to 0 corresponds to everyone having the same wealth, and this represents perfect equality. And Gini equal to 1 corresponds to a single individual that has the wealth of the whole system, which corresponds to complete inequality. In the talk that Roberto Iglesias will give tomorrow, we will see more details about the origin of this kind of measure of inequality. So I will pass very quickly for this part. And also, I'm going through this technical slide very quickly, but if you have questions about this, you can ask me. So I rather prefer to summarize the main macroscopic characteristics of this model. So we can look at the wealth distributions obtained in the stationary state for several values of the social protection factors. Here we plot the number of patients, or the fraction of patients that have a given wealth in the x-axis. And this model exhibits wealth distributions with exponential tiles, and Pareto distributions are not observed in any range of wealth. And in this way, this model replicates the behavior of the low and the middle classes. And this was started also in previous work. But more interesting than this is what we observe in the insects. Here we show the same distribution, but using logarithmic mean. So we can see that the gap between the richer and poorer agents become smaller with increasing of the social protection factor. And this fact can be related to the fraction of agents that will be out of the system in equilibrium, which is also a function of the social protection factor. For F equal to 0 here, all agents except one will end up with 0 wealth, because one of them will monopolize all the wealth. On the contrary, for F equal to 0.5, none of them will be left out of the system, since even those poorest agents have wealth several orders of magnitude higher than the minimum wealth, which is defined here, which is more or less in this region of the diagram. So these Asians are always in the system, are poor, but are in the system. And this is related with this fraction equal to 0 of the Asian with 0 wealth. So in what follows, I will present some of the results of the macroscopic results we obtained, in particular those concerning to the search of correlation between risk and wealth of the Asians. I won't have time to see to present everything, but I think I will have time to these first two, and they will allow me to obtain the critical risk and the optimal risk, as well will be clear very soon. So to investigate how the macroscopic results emerge from the microscopic behavior of the Asians, we construct this kind of density plots in the risk-wealth plane. These plots are simply the final state of a large number of Asians obtained from 10 to the third simulation of 10 to the 4 Asians each one. And these two columns represent the same density plot, but with different scale. This has a linear scale in the wealth, and this is a logarithmic scale. So first, in the left panels, we observe two regions of maximum density, here and here. The region near 0, risk 0, shows that Asians with very low risk reach very similar wealth. On the other hand, we also observe a maximum for Asians with relatively high risk that still preserve some of their wealth, but do not make good transactions. These results led us to conclude that those Asians with a low risk will always preserve a considerable amount of wealth, but they will never become rich. Whereas Asians that have progressively more risk, there are a small number of them that will be able to reach higher wealth, but most of the time they will end up losing almost everything. So the logarithmic representation here in the right column shows also the existence of a critical risk factor, such as the Asians with risk above this value will always end up losing all their wealth when the system approaches to equilibrium. So this is also observed in these figures, but it's more clear in this logarithmic scale. Note that this is changing the value of the critical risk change with the value of the social protection factor. So to be sure that the density plots here are not ignoring some points that are that appear very few times, we made maps, binary maps, in which the pixels can only adopt two values. One, if there is an Asian in this point, or 0 if not. And as you see, the general shape of the distribution of the Asians in the plane continues to be well demarcated, and it's verified indeed that there is no Asian in the darkest regions of the density mapping. Besides, we can use this representation to look at the evolution of the system. And what we see is that the emergence of this critical risk become apparent as Asians with very high risk are then, at the end, are expelled from the system. So this kind of results highlight the importance of studying the dependence of the critical risk with the social protection factor. So we calculate the mean critical risk factor as a function of the social protection. See? These are the standard deviation, and this is the mean value. And to do this, we tracked the transactions of each particular agent until the equilibrium was reached, and we evaluated the final value of their wealth. Each point corresponds to 1,000 systems, and as expected, the critical risk increases with the social protection factor. The division observed here in the plane shows a clear picture of what we consider a loser or a winner strategy. This red region corresponds to those Asians that lose all their wealth before the systems arrive at equilibrium. And this green here region corresponds to those Asians that never lose all their wealth. Moreover, in this green region, we plot a darker region that indicates the successful strategies. This refers to Asians that reach higher wealth values than the average. But this critical risk allows us to divide the plane into phases, those of good and bad strategies. But we can still wonder what are the best ones. And an easy way to study this is to analyze the average wealth per Asian after reaching equilibrium as a function of risk. So this is the average wealth. This is the figure for F higher than 0, and this is the risk. So what we can see is that the maximum can be observed for all values of F, indicating the existence of an optimal risk that allows an agent to obtain the maximum average wealth. It can be also noted that such a strategy will be less effective as increasing F, but this maximum corresponds to the darkest region of the diagram and show the existence of an optimal risk value. For the case of no social protection factor, or is equal to 0, we need to do something different because the macroscopic equilibrium cannot be reached in a reasonable time scale. So the study consisted in evolving 1,000 of independent systems and checking the risk of the richest agent after 5,000 Monte Carlo steps. And in this case, we see that the probability of an agent becoming successful increased with the risk. And this also describes the existence of a winning strategy of the system. It is convenient to have a high risk, such that a high enough wealth can be achieved in a relatively small amount of transactions. And once high enough wealth is reached, interaction with the remaining agents will not affect the wealth of the richest agents in a significant manner. So my conclusions are that the microscopic dynamics of the agent unveil the existence of a critical risk, such as those agents will risk higher than this value will always end up losing everything when the system reaches equilibrium. And this allows for a classification of winner and loser strategies in this model, which depends on the values of the parameters F and R, the social protection factor and the risk of the agents, and also turn out to be scale invariants. Another interpretation of this result is that it is possible to estimate how much wealth you should be risk in different type of societies characterized by the social protection factor to always obtain the maximum possible profit. But even in a society where the market regulation policies favor the poorest agent in every transaction as much as possible, which is F equals 0.5 in this model, there will always be an individual optimal strategy that grants maximum average wealth. In other words, in such society, there are no agents outside the system, but there is still individuals who end up with more wealth than the others, and they are those who have risk closer to the optimum. So, to finish, having found the existence of these optimal strategies in the model, the next step was for us to provide the agent with rationality through neural networks, allowing them to change the risk factor to improve their performance. And this was the master thesis of Julian, and these results are recently published in this paper. I can share if you ask me. So with this, I say thank you very much.
Thank you very much, Fabiana. Very nice work. There are some questions here in the chat by Marcos. One question is that is the total well conserved?
Yeah, it's a sum zero game, exactly, yeah. And this is one of the main limitations of this kind of model, but yes, this is. And yes, the next is from Nuno Krokidakis.
Yeah.
How did you estimate the critical value? Okay, it's not clear. I go back. I have time, I think. So I will go back to. If I can. Okay. This value. Okay. To find this value, I pass very quick for this result. The way to see that this exists, this kind of value exists, is looking at these diagrams that happens at equilibrium. You have a value above which we have no individuals with wealth. Remember, this axis is wealth, with wealth higher than zero. But the way we did the diagram is not this, but we made a lot of simulations. We took an agent, put the system to evolve, wait until the equilibrium, and calculate or register the value of the wealth. When the wealth is zero, we are in this region, and when the wealth is higher than zero, we are in this region. It's just tracking the agents in many simulations of many agents, and looking at the final wealth after equilibrium. And we have two options: is zero, and we are here, or higher than zero, we are here, and the limit is the critical region. We also make a plot. I didn't present this. A plot of the evolution of the wealth as a function of the risk, and we have a very sharp drop at the value R critic, and we average this value. Is clear? Are you?
Okay, he says okay. Okay, you can raise hands to make questions. I have a little question about the minimal value of the wealth. There is values of wealth very small. If you put a minimal unit of money exchange, what happens, or something changes, or?
I go back to the here. Yeah, you need to define a minimum value in this model, and this minimum value we define it as this is my cat, Nina. So we define it the bankruptcy, which is the minimum value that below that agents we stated that they cannot recover from this value. So all agents that in a transaction has less than this value, we set they well equal to zero, and then this agent is out of the system because it has no way to make a transaction. This is the way they are going out of the system, losing a value lower than this minimum value.
And the results are not sensitive to this threshold?
No, the most of them, no. We have I think I can show you a case where we decided to talk. No, it's not here. Here, in this case, we have the average wealth per agent without considering the individuals with with wealth equal to 0. And what we did here is for different moments of the simulation, we plot the average wealth per agent. But here it was necessary to put out this one with no wealth, because the curves are very sensitive to this case. And this was only to show that a local maximum appear in the middle, but we first have that the winner are the risky agents, but they end losing all the wealth. Only in this case was necessary to include or exclude the individuals with wealth equal to 0.
Okay. Any question? Okay, there are a few minutes now, so if you want to add some comment, otherwise we can prepare the next talk. Want to comment anything else, Fabiana, or?
No, just this is a very nice result also that was also observed by Sebastián González, Roberto Iglesias, and Benur Cardoso, and we also analyzed that there are a maximum in the evolution of the Gini index, and it can be also understood in the context of the microscopic behavior of the system, and this maximum that appear here has to do with this kind of behavior where agents first accumulate but then lose everything and transfer the money to the less risky agents. So this is very interesting, but it's most difficult to explain in few words. So I put this out of the talk.
Okay, let's thank very much Fabiana, and
thank you.
Kishore Dutta, the next speaker, can share the screen.
Yeah.
We can wait 1 minute. Just I will take profit to announce Kishore Dutta is from the Handique Girls College from India, and he's going to talk about inversion dynamics. Deception favors a slow inversion. So
Thank
wait
you.
a minute to be on the schedule and to start.
Yeah.
Just in case somebody is entering to see your talk.
Is it visible? My skin is visible?
Yes, it's okay. You want to roll it to see if it works?
Oh.
Okay. It's fine.
No, it's okay.
So you have 15 minutes in total, and when 3 minutes are left, I will tell you 3 minutes, but try to leave this time for questions, okay?
Okay, thank you. So good morning, good afternoon, good evening to all, and it's a pleasure to be part of this workshop. So my presentation is on inversion dynamics, basically how deceptive inversion took place on some centrally organized system like the ampères. So, so basically what happens if we look at the evolutionary track of human civilization. Throughout the evolutionary track of human civilization, the process of inversion is so closely entwined with its result, and the closely entwined, and so inversion, the process of inversion is invariably present, and it gives rise to a very complicated dynamics. So questions arises as how did the relatively weak embedder succeed in capturing a massive centrally organized system through the art of deceit. So in deceptive inversion began from the late Bronze Age, And so basically, when we talk about an ampere, it consists of a well-defined territory, and inside the territory there are provinces, and in the provinces the military powers are evenly distributed, and at the center there will be an ampere who politically controls over the ampere. So if you want to understand in the realm of sociophysics, then how did the relatively weak embedder succeed in capturing a very big or massive ampere? Or how can the consequences of deceptive invasion be understood and quantified in terms of the interplay between competition and cooperation? So it is basically the competition and cooperation that that gives rise to very complicated dynamics. So in order to understand this in the realm of sociophysics, we design a model, simple model, very simple, but it's profound. Its results are very profound. So this is the model basically. So the territory, for simplicity of competition, we consider a circular territory, and the green domains are represented by powerful provinces. So, or you can consider them as military power, and then the red one is the troop of invaders who invades from any arbitrary point on the territory, and as soon as it enters in the territory, it starts deception. So deception, modeling deception is very difficult task, but here we consider the ultimate overall effect. The overall effect is how they initiate deception, or how what is the result of deception. So deception basically triggers internal conflict between two neighboring powerful provinces or military forces. So we impose some rules, basic fundamental rules of sociophysics based on evidences from history or some other literature. So, for example, how the vicious warfare takes place. If two domains, one of them is invader, red one is the invader, and the green one is one of the powerful provinces. If they interact, at the time of interaction, if the one of the domain is smaller, the smaller domain will get annihilated, and the bigger one will survive, but it suffers the casualties. Casualties means the afterward effect. So this way we design a simple model, and finally, so again, so all the processes, physical processes like what we have, coalescence, expansion, merging, everything is there in the model. So I think the slides are not coming properly. Something is happening here. Just a minute. My slides are not coming properly. Okay, this is first slide. Okay, so when deception takes place, so deception takes place in different way. One is strong deceit. In strong deceit, if deception is strong enough, the PP who receives the message can also be the victim of invader deceit. So if you look at the dynamics, let me show you the video. One video I have. What is the video? Okay. Slides are not coming properly. Okay, here. Yes. Let me show you the video. So it is one run of the simulation. So you will see here how the process takes place. So this is the invader. As it enters in the pierce territory, it expands and then initiate the deception. And as a result of deception, two nearby domains interact, and there will be warfare among them, internal conflict, and some of them will get the message. So there are some sensory input in the model. So finally, what you see is the domain who receives the message of invaders, then it will expand and coalesce with other nearby domains. And as a result, finally, what will happen? You will get the outcome. So outcome will be either the victory or defeat. So here in this case, you will see the invader is smaller in size at the point of contact than the than the bigger domain. So finally, it is the victory of the ampere. So this way, we run the simulation several times, and because we are looking at the statistical properties of that. Okay, let me share you the screen. Something happens here. Yes. So I'm sorry, something happens here. Okay. So as the process begin, so this way we simulate the dynamics and we find some results. So the results
sorry,
are.
We are not seeing the file, just your directories.
Stop sharing. Something is happening here. Yeah. Is it visible?
Okay. Yes, yes.
Oh, sorry. Okay. So what we have measured is the cost, defense cost. So we assume that during the expansion of the military power, the expansion rate is proportional. So defense cost is proportional to the expansion rate. And this way, this is the simplest possible case, because in an ampere centrally organized system, the economy itself bears a completely different dynamics. But for simplicity, we assume that the expansion rate is proportional to the defense cost. So, you will see that results are very profound. So, in a single run, the cost, I am plotting cost with time. So it looks like this. So there are defense cost as well as investment cost. Investment cost is the blue line. It is very, very negligible, but defense cost is very high. So we compute the total defense cost in each case. So I am showing here in 5 successive investment. That means 5 successive simulations. And this way we find some results on against the number of investments. And since the point of investment is arbitrary, so we have to run it several times. So we run it around 15,000 times and we find the results. So finally, we compute the capture probability of the embedders. What is the capturing probability of the embedders? So as you see here, these results are completely probabilistic. That depends on the distribution of the powerful provinces, whether they are distributed in a narrow belt or they are distributed widely, or the strength of the embedders. So we consider all possible configurations and we plot them. And from these results we have found some interesting conclusions. For example, for narrow distribution of powerful provinces. So PPs means I am calling it powerful provinces or military powers. So if the military powers within the ampere is narrowly distributed, then even a relatively weak ampere with less number of PPs remain impregnable for slower embedders. So this is very interesting result. And if they are widely distributed, if PPs are widely distributed within the ampere, then a small ampere, small in the sense that there are only few PPs, powerful provinces, remains vulnerable even for slower embedders. So as you see here, if you increase the number of powerful provinces, the capture probability of the embedders goes down and it becomes 0. But economically, it is not viable. In order to maintain large number of PPs in an ampere, there is a problem of economy. So So there is a competition between the economy as well as economy and the survivability. So we, for that reason, we need an optimal defense structure. So we design an optimal defense structure here with only few PPs, the green one. There are 5 PPs, and we compute again, and we found that out of 15,000 simulations, or out of 15,000 invasions, nearly 10,000 events, defense cost is almost 0. So this is in x-axis we plot defense cost, and in the y-axis we plot number of invasions. So the defense cost is almost 0. That means there was no deception. Deception fails in most of the events in such an optimal defense structure. So in most of the events, the empire appears as more resistible in destroying the invaders of any strength and does not allow to initiate the plan of deceit, because the simulation result shows it. There is 0 defense cost. So what is more interesting here is that if a very strong troop of invaders attack on such an optimal defense structure or an empire, what would happen? The capture probability goes down. That means, so this table shows you that for faster invasion rate, the capture probability is the smallest. So that means that we have
3 minutes, Kishore. 3 minutes.
Yeah. Thank you. So it is the intuitive picture of the survival of the fastest fails in such a competing dynamics, as observed in other cooperatively growing populations. So this is one of the remarkable results of our simulation. And we have other interpretations that mimic some historical facts. For example, reducing the cost for deceiver implies increasing the cost for the deceived, as envisaged in Journal of Statistical Studies. So they analyze the data. We have not analyzed some particular data. We are giving some generalized model based on some socio-physical rules, simple rules, and we do not have any complicated dynamics for the economy of the empire. But still, we are able to see that reducing the cost for the deceiver implies increasing the cost for the deceived. That means the model is although simple, it is profound. Similarly, a small empire can survive for a longer period if it fosters the art of deciphering any devious ploys instead of decentralizing the military power. Decentralizing means here the wide distribution of powerful provinces. So a narrow distribution is preferable here. A narrow distribution of powerful provinces is preferable on a small empire, and they will survive for a longer period. So these are some remarkable results of a simple toy model. So thanks for listening, and questions are welcome.
Thank you very much. There are some questions here. Marcos asks, have you compared this model with conflicts in Syria or Afghanistan?
I am not able to see the question. Where is the question? So, okay, in the chat box, I think.
The chat box. But I am reading, have you compared the model with conflicts like in Syria or Afghanistan?
No. It is a general. We are not analyzing any data. But we are basically giving a toy model, what is called a toy model. So, but the model is built based on some socio-physical rules, and the dynamics. When we simulate the dynamics, finally we measure some cost, defense cost, and all this, and that gives us some interpretations. That's it. We are not analyzing any data.
Okay, there is another question here. Julian Giraldo want to ask directly? Julian?
Yeah.
Please.
Welcome.
Julian, who asked here, can you read, Kishore, economical competition can be considered as a way to version this model?
Sorry, I am not getting the
Can you read the question here? It's written, or Julian, can you explain better? I don't know where Julian is.
Maybe
Julian Giraldo wrote this question.
If you allow me to do the question in a better way, so taking into account there is more rare events of physical invasions. Can we in your model you can compare economical competitions between countries like
your question I'm getting. So basically what is happening here, we are just formulating formulation of deception is very complicated in real situation. But if you want to make it more, I mean, it has to be dressed up properly. So, for example, using evolving network model, we can study it more profoundly, or agent-based model. But I am not doing here agent-based model. It is just I am imposing some simple rules, and out of these rules, I am looking at the dynamics, and finally we are getting some historical facts we can explain here. That's it. But there are many opportunities here. We can dress it up properly using, for example, network model and all.
Okay, thank you very much. We need to pass to the next speaker. Can stop sharing so that Marcos Gaudiano is the next speaker from FAMA, Universidad Nacional de Córdoba, Argentina, who's talking about why borders of Palestine, Israel, and Wallonia, Flanders are so different. Can you share, Marcos? Okay. So you have 15 minutes. I tell you when 3 minutes are left, okay?
Yes, but I cannot share my presentation. I cannot.
I can see your presentation.
This way. Okay.
Now it's in another mode. Okay. Yes, it's fine. I think that your microphone a bit low.
Well. Okay. So, do you hear me? Okay. I'd like to thank the organizer for giving me the opportunity of presenting this work that I carry out in collaboration with George Revelli. As you can see, the border separating Wallonia and Flanders in Belgium is by far more regular than the border between Israel and Palestine. An irregular border between two nations and or culturally different group of people is something that contributes to the existence of territorial conflicts. This idea has already been studied. For instance, you can glance the works by Janir Barjam I am mentioning over there. In connection with this serious problem, we studied the Schelling segregation model for minorities. As you know, simple models analyzed under a more proper perspective can sometimes provide interesting lessons. The arranging of pixels on the right basically represents two segregated groups of agents. The minority, which is conformed by the yellow pixels, constituting something 40% of the total. The majority conformed by the blue pixel, and the red pixel are empty sites that are a priori have no owner. They constitute 1% of the total, which models the lack of resources or land. The system evolves according to the Schelling's update rule. If an agent is surrounded by more
excuse me, Marcos, some people is claiming that cannot hear you well, but perhaps you can increase the volume.
It is
the maximum. So I ask the listeners to put your volume.
I'm sorry.
Okay, sorry, I can hear you, but I had to put my volume in the maximum.
So he will move to some random empty place in which he becomes surrounded by comparatively more individuals of his own social group. What's happening? Oh, no, I cannot see the slide. I cannot see the slides. I don't know what's happening. I cannot see the slide.
I see.
I'm sorry. Yes, but I don't like that slide. Oh, what a shame.
Okay.
Oh. No, it's not working. It's not working. No. It is. Oh.
It's another talk.
There is. No. It is automatically rolling the slides.
Well, you can
Marco,
open the
excuse me.
PDF
If you
file.
come closer to microphone, maybe we can hear you better. Put yourself closer to the microphone.
Well, yes, but I cannot roll the slides.
This is better. So you put the PDF in another mode, no in the screen, in this mode, and you can. Is it PDF? Is it a PDF file? Or what?
No.
You can put it in another mode of exhibition.
It is stuck. Whatever oh, I don't know what's happening. Oh, what a shame. Oh.
I suggest to leave this exhibition mode and try another exhibition mode. To share the screen with the PDF open, just this.
I don't know how to leave. Oh. No. I don't know what is the correct button.
Well, I don't know how can I help. Marcos, some idea to help?
Oh, right.
The other Marcos? Can you leave that mode and open the file as a normal PDF?
No, I cannot close the screen, the Zoom screen.
The Zoom
I cannot leave from Zoom. Well, I had to shut down my computer because there is no other solution. What is
Just a minute, please. I see how to solve this.
Oh, Celia, I have a suggestion. Maybe we can exchange the
Yes, I am trying to contact exactly.
and then Marco excuse me, Marco can send us the PDF file so we can handle the PDF here.
Ah, yes, yes.
It's CTP. Would be easier. If you agree, we can do this arrangement.
But Suarez agrees to start now.
Célia?
Oi, sim. Você poderia...
O que você mandar fazer, eu faço.
Oh, que fácil. Okay, so people, Marcos, envía the PDF by email to me so that I handle the PDF.
Célia, I will
directly
start.
And Suarez, you can share your screen and start
Fantastic.
your talk.
Fantastic. Can you see my presentation?
Yes.
Célia?
Yep. Yes.
Yes. Yes.
Yeah. Okay. So I'll put it in full screen mode now. Does it work? Hello?
Yes.
Can you see myself? This is the most important part. So.
No.
You cannot see me. Oh, I see. I know why. I know why.
Not.
Oh, I put myself here. It's very important because I have a joke.
Now I see you, but not the.
Yeah, because I stopped sharing. I stopped sharing. So. Okay. No, I'm still sharing. Is it okay now? All together?
Yes.
Fantastic. So can I start?
Yes, please.
Okay. So good. What? Still good morning, you know, for Brazilians, and good day for everyone else. So very nice to be here. I would like to thank the speakers for inviting me, Célia, Marcos, and Nuno. So thank you very much. It's a pleasure to be here to see you all. I was hoping to see you personally, but unfortunately, it's still not time for that. I hope it will be soon. I had the opportunity. I was a little bit late today, but I had the opportunity to see the last 3 talks already. So they were fantastic, and I was very impressed by the mustache of Sebastian. So I knew that already. So I decided to grow my beard for the last years just to compensate the lack of hair that I had in the top of my head. But it came more whitish than I thought, so than I would expect. But anyway, this is life. I'm still trying to understand what's going on here. I suspect there is something to do with age. So, but jokes apart, let me start the talk. So the name of the talk is Cracking Urban Mobility. And you see all my financial agencies here, a lot of people. The money is not too much, but we can work a little bit. So, so I'll talk basically about traffic jams. So this is the basic idea. So it started a long time ago in 2009 when we published a paper that I had expectations to use it eventually to try to understand and to deal with the traffic jams and urban mobility. And this paper was called Fracturing Optimal Path. It was when we somehow introduced the optimal path crack model. It was in 2009, more than, let's say, 11 years now. And then eventually, this series has 2 episodes. We hope this will be a trilogy, but eventually, more recently, we published a paper applying these ideas to real network roads. And the name of the paper, you understand why, is Cracking Urban Mobility. And it was published in Physical Review Research last year. So the stars of these cities, apart myself, which I'm not sure if you can identify here, is Professor Herman, who helped us a lot, especially in the first work. André Moreira, a professor of my department. Humberto Carmona, a professor of my department too. Ernesto Oliveira is a professor at the Universidade de Fortaleza here in Ceará State. Nuno Araújo, who is now at the University of Lisbon. And finally, Aurelio Wilson, who is in Unilab, a university here in Ceará State too. Okay, so I have many informations I decided to write down here, so otherwise I would forget. Question of problem of age too. So I would like to say that first, we will work with traffic congestion. This is part of our daily life. And an important information here that I would like to draw is that in the top 20 cities in US, it is estimated that average daily commuter, people waste somehow something like 85 hours per year in traffic congestion. It doesn't sound very much for a year, but it's a lot when you're inside the car and under stress. Everybody knows that. So in terms of US, Boston is the head of this list with more than 106 hours a year of average delay. And these numbers can be even worse in other cities like Moscow, London, Bogota, Mexico City, when you can exceed 200 hours per year. So this is a very important problem. Of course, the inefficiency not only impacts on life quality and the environment, but also it compromises. Everybody knows that economic growth, it's important to say that. And without central planning, what do the travelers do? They usually choose the route that minimizes. That's what we do every day now with all these applicatives that we have, like for instance, Waze or Google Maps or things like that. But in any case, it doesn't matter if you use applicatives like that. When a road segment gets congested, you have to choose a new optimal route. It has to be found, whether you know that or not, whether you use an applicative or not. So finally, this is what we thought in 2009, that the optimal path crack model could be introduced, some sort of general framework to understand the resilience of a network infrastructure in general, but our idea is to basically work with traffic jams. So here I show you a typical example. This is a pictorial one, but we took the photograph from this very old photograph. I suspect some people that I know here already saw it before when we used to present the 2009 model. So what we have here is people that have to go from their houses to the factories. But let's say instead of factories here, we have universities, okay? So we are talking about professors. And I would like to make a couple of assumptions here. The first one is that you have an infinite source of people going from the bottom to the top, from their houses to the universities. The second thing is that they are egotistical in the sense that they want to use the optimal route, whatever it is, or whether or not they are already congested or not, or if they know that or not. They always go to the optimal route as long as it's open. And finally, they know somehow that the new route was congested, became a traffic jam because of the applicatives, because of the media. And eventually, if that optimal route is changed, is congested, they will choose another one. So what do you do here? Suppose this is me, an old professor going from the university. So I wake up early and I choose this optimal path here. It's very practical, very quick. And what happens is a lot of old professors like me use the same optimal route. And what happens, this route will eventually congested, where most likely in the segment of the road, which has the largest time in the system. So let's suppose that it was congested here. So other professors, like for instance, André Moreira, one of my collaborators, he wakes a little bit later than myself. So he goes to another new route, which is optimal, according to an applicative or according to himself, his knowledge. So there has to be some party in the beach. He was diverted to that party, but eventually his responsibility came again, and he went back to the route of the university. But of course, everybody used the same route as André, and it was eventually congested. And we keep doing that. Of course, you don't have necessarily to use a completely different one. You can start from that place in the beginning of that route and find a new route and so on and so forth. So eventually you will have so many blocked sites that you will not be able to cross from the bottom from your house to the university anymore. So there will be a congestion, a completely collapse, a completely failure of the system. So what's the questions that we wanted to answer at that time? The two important ones were how and when will the transportation network collapse? And what is the role of disorder on the performance of the transportation network? Of course, at that time, we did only that for synthetic networks. And they were very particular in the sense they were always non-directed ones. So we basically, as I said, perform numerical simulations. So we use square lattices of size L. We use fixed boundary conditions at the top and bottom. I'm going from left to right differently if you want, or in periodic boundary conditions in the transversal direction. And we introduced disorder by assigning to each site, let's suppose it could be a time, but in order to generalize, we use the concept of energy if you want. And this energy comes from an exponential distribution. It comes from this function here, where pi is a random variable which is uniformly distributed in 0.1. It's very easy to show that this is equivalent to choose the energy epsilon from a power law distribution, hyperbolic one, which has a maximum cutoff of exponential of beta. So that's the idea, to use a power law distribution here, but with a cutoff so that you can limited times or limited lengths or whatever, or energies if you want. So our algorithm was very simple at that time. So we used the basic one to calculate shortest path from one place to another. So we used the Dijkstra algorithm, which is a fantastic paper, a single page published in 1959. And we used that to calculate the first optimal path, OP, it's not the crack yet, connecting the bottom to the top of the network. So in the second step of the algorithm of the pipeline, the site in the optimal path, which has the highest energy, is permanently blocked. So, and it's another assumption of our framework model here. In other words, we have an irreversible micro crack that is formed at this stage of the process. In the third step, the next OP is then calculated, from which, again, the highest energy is removed, and so on and so forth. Then the process continues iteratively until the system is disrupted, or in other words, it collapses, it fails. In other words, we can no longer find any path connecting bottom to top. So I show you an example here of the system. Beta is the parameter of disorder. This is very low disorder. So what do you see here in red is the optimal path, which goes from top to bottom every time we want to calculate. And every single very small dot here that you see are those sites in our model which have been blocked after you calculate that optimal path, which is going on in the moment. So as you can see, you increase a lot the number of cracks, micro cracks in the system. The optimal path that you generate starts to becoming tortuous as time goes on, like if we can talk about time, not necessarily, but, and this takes a very long time because the system is compact. I don't want to waste time. So I'll go a little bit further on that. So as you can see here, the system becomes more and more tortuous, and it will eventually crack. So now you can see, now you don't see the optimal path anymore, but what you can see is a singly connected line which goes from left to right of the system. So it connects, and it has some ingredients that I'm going to talk about them in the next slide. You can do the same for a very high disorder or moderate disorder, putting beta equal to 0.6. As you can see here, this is different. As you can see, the system already starts with an optimal path, which is tortuous. It evolves very, very quickly to the steady state. The steady state, I mean, is a steady state in which you don't have anymore a path which goes from top to bottom. But as you can see here, if you use the same levels of disorder multiplied by a given parameter, it's funny to see that you obtain exactly the same singly connected line which goes from left to right. So what we studied at that time was that this crack, or now it's an optimal path crack, which is why, because it became from optimal path by cracking them every time. It has some elements, some important elements. It has what we call here the OPC fracture, which is made by the backbone and the dangling ends, as you can see here. And also it has isolated clusters, which have been shown during the simulation themselves, and are the black spots that you can see all over the system. So as you can see, the system for a small disorder is almost compact. So again, just to remind you, the first optimal path in that simulation was almost a straight line because the disorder was very small. And the last optimal path is some sort of fractal-like line that we will study, and people, we in fact did that and found exactly fractal dimension, which is very interesting. So now you can do finite size scaling results and calculate some fractal dimensions for that. So all you have to do is do simulations with much more realizations of the networks for each different size. In that time, we could do from 32 to 512. And we also use distinct values of the disorder parameter beta. What we found here, where M is the mass of anything, you have three types of mass: the mass of the backbone, the mass of the OPC fracture, and the mass of all cracks in the system. And as you can see, the mass of the backbone, when you calculate that using finite size scaling, you see a number which is 1.22. When the mass of the optimal path crack, which includes the backbone as well as the ciliary structure, which is around the backbone itself, and we found a fractal dimension for this value of beta equal to 1.59. And if you calculate for all cracks for low disorder, what you see is a compact structure. In other words, the fractal dimension is equal to the dimension of the system itself, so equal to 2 in this particular case. So it's interesting to see that this fractal dimension 1.22 has been found in many different models. So they belong to the same universality class of optimal paths under strong disorder. So what generates the optimal path crack, which is the optimal path, also has at strong disorder the same fractal dimension. It comes from disordered polymers, strands in invasion percolation, paths from minimum spanning trees, watersheds as well, hulls of explosive percolations more recently, and optimal path crack, which is our case. So now, since I gave you this outlook of the old stuff that we did in 2009, we jump 11 years for real applications. Not real yet, because we, as I said to you, we used in that particular time non-directed networks. So in order to study real systems, we have to go to directed networks. So far, as I write here, all studies that we did on OPC considered non-directed. So, but road networks have some sort of non-negligible fraction of one-way roads, as we know from our daily life, and which is expected to substantially affect the traffic jams and the traffic dynamics. This is effectively what happens, and we will show it to you. And by contrast to previous static approach, the important things about the OPC here, when you talk about urban mobility, is that it accounts for the dynamics of the rerouting as a response to traffic. I wanted to state that very clearly, to traffic jams. So we are always rerouting as we do daily. So suggesting that this model may be a good proxy, let's see, for resilience of, this is a question I'm putting now. So what do we do here? We investigate the combined role of disorder, and I call here unidirectionality for synthetic roads network first. And we introduce disorder exactly in the same way as we introduced in the non-directed networks system that we studied in 2009. But now there is something different. The links are assigned to be unidirectional with probability P and bidirectional with probability 1 minus P. So when you do that, you see systems like that. These are very small systems in which we did the simulations. So the red lines here, so when P is equal to 0, you have a bidirectional network, road network, synthetic. When P is equal to a number between 0 and 1, you have a hybrid system with, as we found in our cities, with single ways and two ways roads segments. And when we have P equal to 1, the system is fully unidirectional. So as you can see here, the red segments in the road, which are all bidirectional here, this system is much more resilient. So the red lines are those lines, those segments that remain always in the path that you removed during the optimal path crack model. This dashed line here is exactly the crack that you obtained before when the system was bidirectional. And as you can see, we needed here to calculate the optimal path crack something like 15 iterations of the optimal path crack algorithm. So as you increase P, this number decreases, which shows some sort of decrease in the resilience of the system. So as long as you have a larger number of unidirectional segments, the systems become less and less resilient to traffic jams. So this is the finite sizing scaling results and fractal dimensions that we found for this type. In this, nowadays we can do simulations with much more realizations. For instance, with 100,000 realizations, we could increase the system size as well. We can now go to 1,024, and we did that for weak disorder, for instance, using beta equal to 0.002. So what we found here for different values of P, where N of R is the average number of removed links that you do after you finish. This is the average number here. So what you can find here is that when P is equal to 0, when P is equal to, in other words, you have a system which is fully bidirectional, you recover more or less exactly this, or more or less no, exactly the same result that we did for our original paper of 2009, with the difference that here we are dealing with links, but before we were dealing with sites, of course. But of course, this is a detail of the system that should not affect the universality of the, let's say, critical exponents. We know very well that. So for P different of 1, we see that the number of removed links goes to the size, to the dimension of the system, which is in this case is equal to 2. So the basic idea here is that if a non-zero fraction of links is bidirectional, the set of all removed links is compact, as we reported before. So again, I emphasize that the fraction of removed links should be a monotonic decreasing function of P. So for a completely unidirectional lattice, what you can see here is for P equal to 1, this is the only thing. So there is almost abrupt change from let's say fractal dimension equal to 2 of the dimension of the system to another different dimension, which is fractal dimension equal to 0.38. To the best of our knowledge, this is a new universality class for the problem. So for completely unidirectional lattices, the fractal dimension of the optimal path crack is 0.38. So when you do that for a strong disorder, the system is quite different. It's interesting, but again, the results for P different from 1 are consistent, but now with the behavior that we obtain for the optimal path crack fractal dimension, for the backbone of the fractal dimension in the simulations that we did in 2009, 1.22 for this, when P is different from 1. When, for completely unidirectional, we see that the fractal dimension is very close to 0. It's very difficult to show it's equal to 0. This is the number we obtain, so we have to be happy about that. So what you can say about that in terms of resilience, practically speaking, is that a rather small number of removed links is sufficient to block the fully directed lattice, which is subjected to strong disorder. So for synthetic road networks, this is the take-home message, the higher the fraction of unidirectional segments and the level of disorder are, the lower is the resilience for urban mobility. So far, so good. I think this is an important, but more or less, I would say, a predictable message that I wanted to take to you. So let's do it for real road networks. So what do we do here is that we apply the UPC method for 2 metropolitan areas in the United States. Namely, it's Manhattan and downtown Boston, because they are more or less of the same size. And the later is the top, as I said already, is the top one in the rank of North America for time waste in traffic. So for this purpose, what we did here, we obtained the road network structures of both urban areas from OpenStreetMap. We had to pay a little bit for that. And their corresponding average traveling times per road were downloaded from Directions APU, Google, and it was done specifically for November the 21st of 2018 at 4 a.m. So we choose this off-peak data set. Why? Because by constructor it's important that the traveling time should somehow, in a way, reflect the freeway state of the streets, because time is not an important issue here. We want to see the rerouting process taking place as long as the system evolves. So how do we do here? We don't do exactly as we did for synthetic networks because it's not possible. We have to choose origins and destinations. So the OPC, first, in terms of realizations, is calculated for different pairs of origin destination sites. And for each realization, one site is selected at random to be the center of a circle of radius r, like this, okay? So this is the origin. So we choose a circle. And then what do we do? A point on this circle is randomly chosen, and the closest one becomes at the center of this point are taken as the origin and destination respectively. So, but only if the distance between them is equal to this distance L, but with a tolerance of 5%, more or less, if you want. So in this particular case, what do we do is that after we do that, an optimal path is identified among all possible paths during the OPC process. We calculate the OPC process. And instead of using T or L, we had to use a combination. So the optimal path, it's complied in terms of the minimum sum of the ratio between the time of each segment divided by the length of each segment that we are computing during the OPC. So when you do that, before the collapse, now I'm showing already the final simulation that we did for this particular OD origin destination example. So before the collapse, what you see here, all links in black or red in this example here were part of an optimal path that has been calculated during the pipeline, during the algorithm implementation. So at least once. So the red ones are those which are indicated with white circles in the middle, and they are numbered according to the OPC removal sequence. So after you remove 9 segments of this road network, you close any possible connection within that area. Otherwise, you have to go away from the entire city using a different route, but you close any possibility to go from origin O to the destination D. So what are the results that we obtain? So the OPC simulations, so as I said, they have been performed with 2,000 OD realizations for downtown Boston and Manhattan. So we compute for all of these 2,000 realizations, the average number of removed sites for a given distance L. As you can see here, Boston is much less resilient than Manhattan. Why? Because the number of removed sites that you need to collapse Boston is much smaller than Manhattan for any distance between origin and destination. So this is what I write here. Boston is systematically more vulnerable than Manhattan, regardless of the origin destination distance. And this is consistent, thanks God, to the relative positions in the national rank of urban mobility. So here in the inset, what we show is very interesting as well, to show that there is no bias in these calculations in terms of the LPC method itself. So what we found here is that if for each optimal path, we calculate the sum of the segments in terms of T, of the ratio T divided by L, lambda E is the length of the segment removed at iteration I. So if you calculate the length of the optimal path, and you plot this against the number of removed segments that you use to calculate that optimal path, you see that for Boston, you obtain a straight line as well as for Manhattan. So in some way, the fact that you obtain that, and these constants, A and B, they indicate somehow that these systems have some sort of characteristic length associated with their segments that have been removed during the OPC process. Somehow we are saying that these lambdas are selected without bias from the OPC method itself. Okay, so in this particular way, we can see that, according to this result, that the number of removed sites can be a proxy for resilience of urban mobility. So the basic question is, what is the origin of the substantial difference between the urban mobility resiliences of Boston and Manhattan? So we had 3 options at that time. So the first one is disorder. So what we can see here on the plots on the left are the distributions of the ratios T over L for Boston and Manhattan, respectively. As you can see here, they look very much log normal distributions with average times that are similar to themselves, as well as their variances. So in this way, disorder is, in our definition, considered to be weak in both cases. So, and the modest difference between these numbers is not compatible with the large difference that we found in the OPC calculations for the resilience. So in this particular case, we can reject the possibility that disorder is what happens in terms of the different resiliences of the two cities. So the second thing is the fraction of unidirectional links in both cities. For downtown Boston, we found that the probability of unidirectional links is 0.65, while in Manhattan is 0.78. So as you can see, Manhattan has a percentage of unidirectional links which is higher than Boston itself. So, but this is against what we found for synthetic roads, and of course against intuition as well. So what we found for synthetic networks, which is plotted here on the left, is that for similar levels of disorder, it's the opposite what would happen. The resilience of the system should, instead of increase, should decrease with the value of p. So again, the fraction of unidirectional links, they are slightly different, but they do not show why the origin of the substantial difference between the urban mobility of both cities. So we again reject this possibility. The third one, and the last one, is the presence of intrinsic spatial correlations. Why they are there? Because these cities that have not been planned randomly. They have been planned by people who wants to make it better, to optimize something in some way. As we know, we are not experts. I am not an expert on that. I'm trying to understand it from a statistical mechanics point of view, if you wish. So what do we do here in order to understand if we cannot quantify this? It's very difficult to quantify the presence of intrinsic spatial correlations, but it's very easy to suppress them. So that's what we did. The effect of suppressing them, how do we do that? By shuffling the values of the ratios T over L among randomly chosen pairs of road segments in this case. So when we do that, when we apply this shuffling procedure, what we see here is the curves of the number of removed sites against the size of both cities. They somehow collapse to a single curve, which has these two curves here. Okay, approximately collapse, if you wish. So it's interesting to see as well that the values of the number of removed sites systematically increase for Boston and decrease from Manhattan. So it's a particular feature of the OPC that it can capture negative as well as positive effects of the spatial correlations. So in this particular sense, we can say that the reason for the difference in resilience of both cities is the presence of intrinsic spatial correlations from the origin of the road segments themselves. I'm almost finishing. There is only 2 slides. Celia didn't warn me yet, but the final question I would like to ask you is that, okay, so far, so good, but it can be used as a proxy, but can it be used somehow to enhance urban mobility? Is there a way that you can use this technique to improve the resilience of a city to traffic jams? So a possible answer for that, as I wrote here, is to prioritize rerouting and structural improvements based on what? On the identification of those road segments that are more frequently appearing among the first removals of the OPC sequences. So that's what we do here. So you see for downtown Boston and Manhattan, what you see here is that these are the road maps of the 2 urban areas, and where the highlighted road segments, they are thick and red in this particular features here. They correspond to all those removed first, considering all OPC samples performed with a fixed distance, in this particular case, 2,000 meters. So that's what you have when you calculate the OPCs and you plot only the first removals of the OPC of the optimal paths that you have to use. So it's funny to see that for downtown Boston, you only need a 5.4% of all road segments to be removed, and only 10% of the values for Manhattan. So that they are always repeating themselves if you insist in more simulations of the OPC technique. So if you plot the cumulative dependence of the percentage of all first removals in both cases, you see that the percentage of all first removal elements, they reach 100% for Boston, close to 6%, 5.4, and close to 10% for Manhattan. So which shows again that you need very little, of course, rerouting. This is little, but it can be very expensive. But you might somehow pinpoint those road segments which are can be prioritized and can be changed in a way, for instance, by changing them from unidirectional to bidirectional in your system. So these results, of course, this is final message. They suggest that as compared to Manhattan, you need only a relatively small number of potential local changes, as I told you, and this might be very efficient in improving urban mobility. It has to be made in order to be checked. Thank you very much, and sorry for the time I consumed.
Thank you very much, Suarez. The time was perfect.
Oh, wow.
So there are some questions here in the chat. I don't know if you can read them directly.
I will stop the sharing. No? Do I have to stop sharing to
not necessarily. Not. Oh, there are many questions. First, I think that is by Marcos. New York and Boston are large cities. What about middle-sized cities? In Brazil, for instance, cities which are not really big and the traffic is a mess.
Okay, so this is episode 3 of the cities. I need more stars and students to do that. But this, thank you for the question. You're absolutely right. So these are peculiarities that we have to take care of. I hope it works.
Okay, there is another question by Sebastian. The collapse of the two cities were reshuffling seems to point to a universal feature of the OPC. Can you say something?
Yes. Yeah, the word universal may be too strong because when you talk about phase transitions and critical points, no? But I agree with that. And this is something that I would really like to be true. And it appears so. It's funny because as I showed to you in the last slide, in the last question, that we wanted to optimize, to enhance the optimal the urban mobility. Boston, downtown Boston and Manhattan, they have very different road network structures. So it's not by coincidence that those two curves after reshuffling show similar results. No? It cannot be.
Okay. So another question. Daniel Estariolo, what about the number of or density of cars for a given map?
Yes. This was one of the questions of the referee, but I'm sure it was not done yet.
It was the referee.
Daniel, this is a difficult question. So I wasn't. So he disclaimed already. Thank you. I know.
I wasn't the referee.
No. But, this is not a tricky question anyway. This is why I said immediately it wasn't you. So, but anyway, so this is an important question because we cannot deal at the same time with the rerouting in a dynamical way. That would be the perfect way to deal with the problem, like we do every day, you know. But we wanted first to have the possibility to calculate some index, which is in this case the number of removed sites, as an index for resilience. And that's why we did simulations for off-peak times and lengths. We had to calculate the time to cross from one place from one origin to destination. And we decided to do that for off-peak so that we could see the evolution of the traffic jams in a slow motion way. But you are right. I'm not sure if this is done in a very quick, like in the rush hours, we will observe exactly the same behavior. This has to be tested. Thanks for the question. It's very important.
Thank you. Very nice talk.
Thank you.
Okay, thank you very much. We will have a break now and continue with the poster session at 12:30.